Welcome to this explainer. Okay, today we are unpacking a fascinating high-stakes puzzle in aerospace engineering. We're looking at the core design trade-off for propulsion systems in nanosatellites. Because here's the thing, when you're building the smallest, most advanced spacecraft in orbit, you don't have endless space and you certainly don't have endless power. Every single choice is a massive compromise. So we're going to dive right into how engineers make the ultimate choice between chemical and electric propulsion.
To truly wrap our heads around this engineering dilemma, we first have to ask ourselves a very practical, honestly kind of wild question. How exactly do you steer a satellite that is literally the size of a shoebox? I mean, when you're hurtling through the vacuum of space at thousands of miles per hour, making precise orbital adjustments is absolutely critical. But you can't exactly cram a massive rocket engine inside a tiny metal chassis. The physics of propulsion have to be radically miniaturized, and that miniaturization forces engineers into some incredibly difficult design decisions.
So let's set the stage. We are talking about the classic 3U to 6U nanosatellite arena. And man, it is incredibly cramped in there. Internal volume is severely limited. I'm talking about every single cubic centimeter being fought over by avionics, the actual scientific payloads, and of course, propulsion. Mass is strictly capped too, meaning every single gram counts towards your mission objective. And power? Well, you're entirely reliant on whatever surface area you have on those little deployable solar panels to generate continuous energy. It is an environment of extreme, unforgiving architectural constraints.
Inside this claustrophobic little footprint, aerospace engineers are forced into a heavyweight bout. It's the ultimate design trade-off for a propulsion system. On one side, you have the chemical thruster assembly, which typically relies on hydrazine propellant. And on the other side, you have the electric propulsion system, specifically a Hall thruster running on xenon gas. Both of these completely different systems are fighting for the exact same precious real estate inside that tiny chassis, but they go about generating thrust in totally opposite ways. To really compare these two contenders, we have to strip it down to their fundamental physics. Chemical propulsion relies on direct combustion or decomposition. It's essentially creating a highly controlled explosion to physically push the craft forward, brute force. Electric propulsion, on the other hand, takes a completely different path. It accelerates plasma via continuous ionization. Basically, it uses electrical power to strip electrons from a gas and then magnetically accelerates those ions out the back. So, it's controlled explosions versus highly tuned electromagnetism.
When you look at the actual hardware, the difference is night and day. With the chemical thruster, it's all about combustion energy expanding rapidly through a nozzle throat to create that exhaust velocity. It's fire, but then you look at the electric thruster and there is no fire. Instead, you have an anode and cathode working within a magnetic circuit to create an ionization zone. It produces this elegant, glowing beam of plasma. Two completely distinct, fascinating ways to accelerate mass and generate that all-important thrust.
But here is where the reality of this trade-off really starts to hit home. When we talk about the thrust generated by that futuristic, glowing blue plasma beam, aerospace engineers literally describe it as the gentle breeze. The actual physical force it produces at any given second is microscopic. To put that into perspective, the thrust from one of these miniaturized electric engines is roughly equivalent to the physical weight of a single piece of paper resting on the palm of your hand. That's it. It is almost completely imperceptible.
And these drastically different thrust profiles completely dictate what your satellite can actually do. Chemical systems act like a fire hose. They deliver an immediate, massive spike of thrust energy. That rapid response is absolutely vital if your satellite suddenly needs to dodge a piece of space debris or make a large, rapid orbital change. Electric systems, they're that gentle breeze. They deliver microthrust over an incredibly long time scale. They're absolutely perfect for gradual orbit raising or long-term station keeping, but completely useless if you need to move out of the way of something in a hurry.
So you're probably wondering, if electric thrust is as weak as a piece of paper, why on earth would any engineer ever choose it? Well, the answer lies in one absolutely crucial metric, specific impulse, or ISP for short. This is basically the holy grail measure of a propulsion system's efficiency. While your standard chemical systems might give you an ISP of around 200 to 300 seconds, electric systems boast a staggering specific impulse of 1,000 to 8,000 seconds. It is a massive, game-changing leap in efficiency.
That massive ISP totally rewrites the lifespan of a nanosatellite. Because chemical systems have a lower relative efficiency, they consume their propellant incredibly fast. You get a huge spike of energy, but your active maneuvering lifespan is super short. Electric systems, driven by that high ISP, feature a highly sustained, hyper-efficient burn rate. They just keep going. They accumulate those tiny, paperweight amounts of thrust over weeks and months, which ultimately adds up to massive total velocity changes over a very long mission duration. And because of this massive efficiency gap, we have to talk about the Tsiolkovsky rocket equation, the fundamental math that governs spaceflight. It dictates drastic differences in how your internal volume gets used up. To get any significant velocity change out of a chemical system, you need a massive, bulky propellant tank. That immediately triggers a red alert because it quickly eats up a CubeSat's tiny spatial limits, leaving barely any room for your actual payload. But electric systems sip their propellant so sparingly that you get a highly compact tank. That unlocks huge mass and volume savings, leaving abundant room for better electronics and bigger payloads.
But as we know, engineering is literally all about trade-offs, right? Unlocking all that electric efficiency and saving all that internal volume introduces a brand new, incredibly strict bottleneck: power. The electric thruster requires constant, heavy electrical input. But remember those constraints we talked about earlier? A 3U to 6U satellite has highly limited solar panel surface area. You are demanding continuous power from a system that really struggles to generate it. This forces engineers to rely on long battery charging cycles just to get very short periods of thrust. Chemical systems, by the way, bypass this headache entirely, since all their energy comes directly from combustion.
So, let's pull all this together and tally up the final scorecard for this design trade-off. It's a perfect matrix of compromises. Chemical gives you high immediate thrust, that fire hose, with very minimal power demands. But it comes at the cost of terrible efficiency and a heavy propellant mass that completely eats up your volume. Electric, on the other hand, gives you exceptionally high efficiency and a brilliantly compact propellant mass, which enables those ambitious long-term missions. But it forces you to operate with low, gradual thrust and introduces a brutal electrical power bottleneck.
So, how does this actually play out when you're planning a mission? Well, ultimately, architecture has to follow physics. You have to dictate your propulsion choice based on your most inflexible constraint. If your objective absolutely requires immediate, rapid maneuvers and you simply don't have the electrical power to spare, you have to choose chemical propulsion. But if your mission demands high total velocity changes over time, like a major orbit raising, and your CubeSat design can handle supplying the continuous electrical power, then you go the electric route.
So the next time you look up at the stars and imagine the next generation of these incredibly complex nanosatellites navigating the void of space, think about the intense engineering battles fought inside those tiny metal boxes. The ultimate design trade-off between the immediate volume-hungry fire of chemical propulsion and the highly efficient, power-starved plasma of electric propulsion really leaves us with one final fundamental question: what will your mission require?